The space between two notes in any kind of scale is called an interval. An interval can be the distance between two adjacent notes or two notes farther apart. The tuning system that most modern instruments use today is called equal temperament. One of its breakthroughs in tuning standards was figuring out a mathematical way to calculate every step up in pitch as an equal interval. Half steps, or semitones, measure this equal interval distance in equal temperament. Enharmonics, or two notes that represent the same pitch, are in fact equal in pitch and are the same half-step interval in equal temperament. Alas, Pythagorean tuning does not have this luxury. Pythagoras and his followers were really big into numbers that could be derived from simple whole number ratios.
That sounds a lot more rational to me.
Consequently, their step-ups in pitch have different values for each enharmonic pair. In Pythagorean tuning, a natural to a flat is called a diatonic half-step and is flatter than an equal temperament half-step, and a natural to a sharp is called the Pythagorean apotemy and is sharper than an equal temperament half-step. Finally, the last step at the end needs to be
Fudged?
tempered down to fit inside the indisputable pure tone octave ratio of 2:1. An equal temperament half-step is equal to 100 cents, the diatonic half-step is equal to 90 cents, the Pythagorean apotemy is approximately 113 cents,
and the Pythagorean comma results when the 12th interval in the scale
that should equal a tonic actually overshoots it, representing a 23-cent discrepancy, or when enharmonics don't quite line up. More on this later. An interval's measure of sense is directly related to its level of sonnets. Intervals can sound consonant or produce in a harmonious tone, such as in a Pythagorean perfect fifth interval, an equally tempered octave, or Pythagorean perfect fourth. They can also sound dissonant, producing a tense or uneasy tone, such as in a tritone interval, a Wolf fifth, or Pythagorean octave with the comma included. Dissonance between intervals can be deliberate, as is the case with the tritone, or it can be embarrassingly accidental, such as when Pythagoras' math doesn't work out as he hoped. A couple cents is not very noticeable to the human ear. The Pythagorean perfect fifth at 702 cents and the equally tempered perfect fifth at 700 cents will sound the same to 99.9% of the population. A really trained ear might be able to detect a 5 to 10 cents difference in an interval. However, most of us can pick out a 23.5 cent difference between two pitches, such as with the Pythagorean comma. An uncorrected Pythagorean octave totals 1,223 cents though, or 23 cents sharp. And as we learned on the banjo, 23 cents or a 1.014 coefficient surplus is a noticeable difference. So with Pythagorean tuning, the earliest documented tuning system there is, the octave is tempered down to equal a 2:1 ratio. To put it in another perspective, a 23-cent offset is about a quarter step difference. This translates to a small but noticeable fissure between pitches, since even an untrained ear can gobble down a 25-cent difference.